Vivek Borkar from IIT, Bombay, and I thought he was going to give a talk, but instead he's going to give some miscellaneous gossip.
So, thank the organizers for inviting me here. So, this talk is kind of a disjoint union of several small bits and pieces from all over, and my apologies to those who have heard me before on this. I mean, the parts of this I have talked about elsewhere. So, let's start with something simple, which is the sort of vanilla gossip. So, that's the iteration, which is simple averaging scheme. So, P is a stochastic matrix. So, xn plus 1 is the average of xn with respect to the rows of the stochastic matrix, and this is the incremental version with the degrouped model for opinion formation. In either case, it is not hard to see that they will converge to the average of the initial condition with respect to the stationary distribution of P, and that is what we are interested in. And what I want to look at is the stochastic version. So, instead of doing this deterministically, at each time n node I just picks a random neighbor. So, neighbor being somebody for whom the probability Pij is strictly positive, and then takes a weighted average of his own value and what he observes with the neighbor. So, this is the iteration, and what one can do is add and subtract one step conditional expectation and reduce it to something which is looks almost like the degrouped model, except that there is this additional term which is a martingale difference sequence, which you can think of as noise, and it starts looking like a constant step size stochastic approximation. Then again fall back upon the standard ODE method of analyzing stochastic approximations and write the limiting ODE, which is this, and this also dutifully converges to what you wanted to converge to, which is the stationary average of this. But there is a problem with the stochastic approximation, because this ODE is marginally stable. This sort of it is not asymptotically stable, but there is a kind of degenerate direction along which namely the eigenvector of P minus I, which corresponding to 0 eigenvalue, that is the constant multiples of say 1 1 1 1, the boldface 1, and because of that so the traditional ODE analysis of stochastic approximation depends a lot on asymptotic stability, and which is not present here. So, what you get finally is that you do I mean you get consensus, but not convergence to the desired value. So, you will go to some point on the eigenvector, but not necessarily the one curve which gives you the stationary average which you are looking for. So, what we did is to propose something else based on, again this is adapted from elsewhere, from the reinforcement learning literature. So, look at this equation, the Poisson equation, and so this those who work in dynamic programming are used to this, except that there is no control. So, it is a linear case, and instead of the cost I have plugged in the initial value, and one knows all this, that if P is irreducible, then you have a solution V beta, where beta is in fact the quantity you are looking for, and V is unique up to an additive scalar. And then there is also this relative value iteration algorithm, which goes back to 63 in fact, and this so what one does is something like value iteration, except that this not being a contraction, the convergence is not guaranteed. So, you subtract an offset. So, this is one particular choice, does not have to be this, but this is a kind of popular version of relative value iteration. So, what one can do is the stochastic approximation version of this. Okay, so this was for the controlled case. There is an unnecessary min over u here. In the present case, we do not need. So, it reduces to something which looks like this, and here indeed one can have a convergence as desired, and the reason being that subtracting this offset stabilizes the algorithm. So, if you write the limiting ODE, it is actually an asymptotically stable ODE, because you are subtracting from the, you are killing basically the degenerate eigenvalue of the P minus I by plugging in this object. Yeah, I forgot to mention, there is also, as I said, this is not a unique choice. One can replace any f of v with these properties. In particular, the arithmetic mean also works, and that is often convenient, because as you might have noticed, there is one problem with this. Okay, let me say what's good about it. This works very fast, and even with the constant step size, which doesn't guarantee probability 1 convergence, the error is negligible. But then the problem is that it's not fully distributed, that the v I naught has to be known to everybody, and you have to either sort of use some other scheme to broadcast it on a faster time scale, or as I said, one can use the averaging of running average on a faster time scale, which is another kind of stochastic approximation algorithm. So I won't get into the details of that. So there are some trade-offs. Okay, and one can also consider multi-hops. So by that I mean that either you pick the value your neighbor has, or pick a value say your neighbor's neighbor had, and your neighbor had pulled it and stored it for you. So you can go up to 2 hop neighbors, and that is some complications. One has to make sure that you replace original p by some modified transition matrix, and you have to make sure that the stationary distribution remains eta. There is some minor bookkeeping needed here. And the other trade-off is that each time you sample a particular neighbor, say j, you are not pulling his value. So you are sampling your neighbor at a lower rate, because sometimes when you actually sample him, you are not pulling his value but some other value which he has stored. So that increases the corresponding delay, and the delays lead to an error of the order of the step size. But on the other hand, you are improving the connectivity. I mean, you are sort of reaching further, so you expect faster convergence, and that's what, at least on the moderate size problems, we observed that it worked much better, and net loss due to the errors caused by additional delays, etc., was not much. Okay, so let me get to something a little more complicated. So what if you want to actually influence the value it converges to? So the idea here is that you are able to convince some nodes to freeze their value at a pre-specified level, and then of course the rest of them will converge to that value. And the problem is how to do this optimally. I mean, which nodes should be influenced? So there are several variations of this problem. So the first one is this, that I just pick some k nodes and freeze their value at some pre-specified. I mean, it doesn't have to be the same value, but for simplicity, let's assume that you freeze them at some fixed value c. Then the dynamics changes to this. So let me just take the so suppose the last k nodes are the ones which I froze. So first n minus k nodes remain. I mean, they continue to learn based on their own estimates and neighbors. So let p tilde be the square submatrix corresponding to the unfrozen nodes, and p bar the one which corresponds, whose rows correspond to the unfrozen nodes and the columns correspond to the frozen. So you just separate out the first n minus k elements of the iteration, steps of the iteration, it reduces to this. So now you have this p tilde and the p bar here, and p tilde is now a substochastic matrix. I shall assume that this is irreducible, which is a little ad hoc, but the idea is that k is relatively small compared to the size of the network, and you are not really perturbing the communicating properties of the network, and certainly it simplifies analysis. Okay, so this will converge to what you want it to converge to, and the problem is to optimize the convergence rate over the choice of the set of k nodes whose opinions you want to freeze. So this becomes a difficult problem. So I should mention that now, I mean, it's a lot of work on optimizing the second eigenvalue, because it dictates convergence to stationary distribution. This is a little different because I have a substochastic matrix and I am actually interested in the top eigenvalue. So there are a couple of methods we tried. The first is just embedding it into a continuous problem. So define p prime theta as p times theta, where theta is just I mean, ideally it should be 0 or 1, but you allow it to take continuous values with this constraint. So any integer solution will correspond to the original problem. So now lambda is a function of this vector theta, we can derive expression for the partial derivatives of lambda with respect to the theta I. So just write the say left eigenvector equation, right eigenvector, and differentiate say this one, and then right left multiply by pi. And the standard kind of steps one goes through in perturbation analysis, and give a clean expression for gradient of lambda with respect to theta. So with that one can do a projected gradient scheme, except that the projection is now on intersection of convex sets, for which fortunately this ready-made algorithm available due to Boyle and Dijkstra and separately Hahn, which I haven't gone through the details. Basically, see, this alternating projections works for subspaces but not for general convex sets. So they sort of simultaneously tweak both the primal variables and a set of dual variables and prove convergence to the projection of the intersection of convex sets. So that's what we used. Okay, now this is the second method we tried was the following. So we have this interpretation of the eigenvalue as basically the decay rate of the tail probability of exit times. Now just take that as a kind of spiritual motivation to just replace the original cost criterion by this mean exit time from the unfrozen set with uniform initial distribution, and that leads to something which is supermodular. That again is not an easy problem, but there's a good approximation algorithm again off the shelf which we can use, which is the greedy algorithm. And from this Nemhauser, Wolsey, Fisher work, one knows that it's basically 1 minus 1 by E optimal. So you have this kind of a bound, and the algorithm is simple. Just one mild technical point, that because there's a I minus P inverse involved, one trick we use was this Sherman-Morrison-Woodbury formula to beat down the computation. And the interesting thing is that this worked better than the nonlinear programming, although it's far more ad hoc. In fact, the nonlinear programming version we tried for with multi-starter with several initial conditions and then pick the best, and regardless, this heuristic tended to do better. One can extend this to, you can allow for an adversarial action as well. Incidentally, this was initiated by some project I had from General Motors, and they were interested in basically advertising on the social network. So you can imagine say a situation where trying to sell General Motors cars, and say Japanese are trying to sell Toyota, and so there's a certain simplification here. If there are several agents trying to sell several different things, it's not necessarily a zero sum situation, but the non-zero sum again becomes too hard to analyze. So you just sort of club the everybody else as a common enemy and consider the zero sum case, and that more or less can be fit into the framework one had earlier. Okay, so that was one part of the algorithm. So I'll talk of three levels of problem. The first one, of course, is to identify k agents and freeze their probabilities, freeze their values. The second problem I consider is you can also tweak the probabilities of the unfrozen agents in addition, and so index the transition probabilities by this control variable u. But I'm not at this point, I am not considering a full-fledged control problem, but treat it more as a parametric optimization problem. So just do a parametric optimization rather than a dynamic optimization. It will reduce to a control problem, but through a kind of sleight of hand. So okay, so PU is a parameterized transition matrix, as now some GI UI is the cost of using control UI. So UI is a control which you use in state I. This Hj nu j is the cost of fixing j's opinion at nu j. So these are the j bigger than m, these are the frozen agents. You want to freeze their opinions to nu j, and the rest you just want to manipulate the probabilities. Okay, so this is some just technical convenience. So for the unfrozen agents, these things don't feature at all, you just set them to 0, and for the frozen agents this doesn't feature at all, so you set it to 0, so that they are defined on the entire state space. I'll also assume that this object is finite, and you have this kind of optimization algorithm subject to this constraint. Okay. So this is sort of you want to maximize the average rating of your product, say, subject to minus the cost you incur, and this is the relationship which binds the variables. Okay, so again one can do, I mean, when we did this, derive the gradient expressions and so on, it become horrendous, so just leave it, and then use what I call engineer's license, which in actually the second time I am using it. I also used it once before to use the greedy scheme for the discrete optimization problem, but here what one does is to convert this parametric optimization to a related Markov-Odyssean process. So I consider a controlled Markov chain. I have added, so my state space was capital N. I have added one dummy state, which basically an absorbing state. So just the convenience, and put all these quantities equal to 0 on that state. Tau is the first time you hit the frozen set. Okay, so from all the frozen states you get absorbed into the dummy state. Okay, continue to assume irreducibility, and then consider this problem of maximizing the reward up to the first exit time from the set of unfrozen states, starting with uniform initial distribution. And now this Zeta is the control sequence. Now this may look a little different from what I started with, but not really. Okay, so the optimal choice of the nu star turns out to be a simple optimization problem. Just take the maximizer here, and thereafter one can forget that, forget this, just plug in nu star everywhere. So it's essentially a problem of optimizing this running cost given by the G up to summed up to the first exit time, and yeah, so this C gets fixed because of this. If you look at it carefully, it turns out to be equivalent. So we had this kind of object earlier. Now I am replacing it by a weighted sum, and this of course is the mean time spent in state I, parameter of the U, of course. So the mean time spent in state I up to the exit time. So one can, I mean, having already done this, one can of course rationalize it. One can think of that as a centrality measure, I mean some measure of how important node I is, and since it is our job to define the optimization problem, we can invoke this piece of wisdom and switch to the new problem. The advantage being that now it is something familiar and you can fall back on what we already know. So it is reduced to something familiar. So you can write down a dynamic programming equation, and there are any number of off-the-shelf techniques for handling it. Okay. Now the third level. Okay, sorry, that's one thing I should mention. You can also, as I said, you can do a game version of this, assuming adversaries, and the zero-sum game one can handle without too much additional complication, but non-zero of course is much harder. Okay, so before I go to the next level of complication, there is something else we tried, which is the following. So we have this kind of a dynamics. So this is some convex combination of something we had earlier, which is the gossip-like object, plus some dynamics, some learning of the agent on his own. Okay, so these are some weights basically on peer pressure, say, and this is his own inclination or learning, and gamma I of course is step size or learning parameter, and the ODE okay. So I also assume that if there was no interaction, it would be just some scalar equation for each person. I assume that this has bounded trajectories, which being the equation being scalar ensures, if it, assuming of course that it is well posed, it ensures that it will converge to some equilibrium, and I assume that the set of equilibria is kind of finite. Okay. So what happens when they start interacting is the issue. So now with interaction, it's this kind of equation. So this again, it ends up, I mean, it's easy to see that it's a cooperative differential equation in the sense of Hirsch. So, for almost all initial conditions guaranteed to converge, and again if all of them converge to a common value, I'll call it a homogeneous equilibrium, otherwise I call it mixed equilibrium. So, what our interest we're interested in the situation where we get a homogeneous equilibrium. Now, that is without opinion manipulation. So, if you also have the opinion manipulation as before, that you freeze the opinions of a small subset to some value x star say, then the dynamics changes. Now, sorry, this should have been P1 here, it is a substochastic matrix, and F is just sorry not don't seem to have defined F. F is just this F1 F2 dot strung together. So, I assume common F for all of them. So, this is the only possible homogeneous equilibrium that one can prove for the opinion manipulation case. What you also get is that if there is a lot of interaction, this is the only possible equilibrium, and you get consensus. But if there is little interaction, they will converge to some neighborhoods of the different equilibria of F, but not necessarily the same. And that is basically from Hirsch. That's not, I am not saying anything new. Hirsch plus some results from perturbation of differential equations. Okay. So, this is what we observed empirically. So, this is interesting, but we do not have any analysis of it. So, for without opinion manipulation, for low values of alpha, there is low interaction, you get total disagreement. Now, for a lot of interaction, you get the worst possible consensus in terms of some appropriate cost measure. And we took a gradient scheme, so we just look at what values of F are attained at that particular equilibrium. So, F was minus grad of G say, and we look at what values of G were attained at the common equilibrium. And there are two transitions. So, there is a total disagreement above some critical level. Suddenly there is a consensus on the best possible common value, and if you increase the interaction further beyond again some threshold, it just breaks down and becomes terrible. And with opinion manipulation, of course, there were just two regimes. There was a disagreement, and then beyond a very well defined threshold, there was consensus on the desired equilibrium. Okay, so let me get to the next level of complication here, which is the full fledged control problem. So, now I plug in ut and write down this nice control problem with you want to stay close to say x star. Okay. So, this so there is no cost on control, and this turns out to be somewhat well behaved. So, one goes through the usual motions of deriving the Hamilton-Jacobi equation, and what one gets is something reasonably sort of clear cut optimal control policy, which tells you that you should push towards x star in some sense. If you put cost on control, then there is no transparent interpretation. One has existence and characterization in terms of AGB equation, etc., but that is about it. And the same is true for the game variation, game problem. One can write down the Isaac's equation, talk about its existence and verification theorem and so on, and but nothing explicit. Okay, now this is the last problem I want to discuss, which is again changing track completely. So, a connected graph, and I want to given a non-negative matrix Q, irreducible non-negative matrix with some Perron-Frobenius eigenvalue lambda, and I want to find the Perron-Frobenius eigenvalue. Okay. So, what I do, so the idea is to give a gossip-like scheme to do this. So, I write Q as I pull out the row sums and write it as D times P, where D is the diagonal matrix and P is the stochastic matrix, and this transition matrix of an irreducible Markov chain. And suppose I take some probability vector weights alpha j, which actually they do not have to add to 1, but some positive weights, and this is some variant of the power method. In the usual power method, one normalizes by the norm, but this also works. and in fact one can think of it as a sort of uncontrolled case of relative value iteration for risk sensitive control of Markov decision process, which I had worked on with Sean. There he is. Okay. So it's again same old trick, and one can show that this will converge and so on. But what I want now is a gossip version. So again at time n plus 1, the agent I samples a neighbor according to pi and does this above iteration. Again add and subtract one step conditional expectation so that it becomes a stochastic approximation algorithm, and this is the algorithm I want to analyze. And now the right hand side is nonlinear. So one can think of this as a multiplicative counterpart of whatever the average started with, that was the value iteration, relative value iteration for average cost, but because it's a multiplicative problem, it becomes a nonlinear situation. And okay, so one small bit of detail, one can sort of, as I said earlier, one can sort of track the running average. This x bar n can be, I mean, in principle this is something which everybody has to know, so that it's no longer distributed if everybody knows this average, but that can in principle be computed on a faster time scale by a separate stochastic approximation algorithm. So modulo that catch, let me analyze this. So what you get, the limiting ODE ends up being a nonlinear ODE, and one can show that indeed it. So here the analysis does apply the ODE analysis, and this is a nice ODE, and one can show that it converges just to a particular point on the eigenvector. And the analysis I won't go into detail. It's interesting because it looks at what one has to do. Perhaps there may be some other way also, but the way we do is just take the linear case. Suppose so this will eventually converge to the eigenvalue. So consider the case when suppose you knew the eigenvalue, you plugged it in. This becomes a nice linear case, and this one can show is a non-expansive operator, and that ensures the convergence of this ODE to an appropriate point on the eigenvector. And then what one does is to one can sort of map solutions of this differential equation with solutions of that. There's a one-to-one way of going back and forth by both time scaling and sort of spatial some spatial weight. So there's some slightly messy calculation involved, but one can go back and forth and show that if this converges, this will converge, and vice versa. So not necessarily, not to the same point necessarily. But the interesting thing is this is marginally stable. So even if you knew lambda, this is non-expansive, so there's a degenerate direction, and therefore the stochastic approximation scheme cannot be guaranteed to converge to the point you want. But this is much more stable. One can show that, in fact, because this is kind of, I mean, one way to think of it is if you scale, say, x tilde by x tilde, this by alpha, this also scales by alpha, and alpha alpha cancel, whereas this remains, oh, there's a tilde missing. So this stabilizing factor remains unaffected. So suppose x tilde was blowing up, then this thing wouldn't be perturbed because the blow up factor would more or less cancel each other, whereas this would become very kind of strong drift towards the origin, and it would pull it back. So even in the case when you know lambda, this is a far better scheme than this, much more stable. And okay, so one should in principle consider asynchronous case. There that leads to extra complications. There's various ways of working around it. One is to replace an by a new I comma n, where nu is the local clock. So the new I n is the number of times I has performed, node I has performed his iterate till time n. That plus some additional conditions on n. So the idea is that sum of ai should increase logarithmically. So 1 by n log n, such things are good, but 1 by n raised to 2 by 3 is not good. So with this kind of thing, what one can show is that the limiting ODE is in fact is a time scaled version of the original ODE, and therefore has the same asymptotics, and the same analysis applies. If you use more general step sizes, it is doable, but analysis is much harder. So, one more thing which more or less is completed with what I have been doing with a student is considering reinforcement learning on a graph with a gossip component. So, specifically we are considering the TD0 algorithm, and the part where you do averaging with respect to the probabilities, you also add another layer of averaging with over your neighbors as well. And what one gets is what one gets is slightly improved error bounds. One doesn't have an expression for error here, only has bounds, and one gets better error bounds, which in itself doesn't prove that it is better, but the simulations show that one does in fact get lower fluctuations. Okay, so it's a joint work with lot of people, and most of them are now in different place than where they were when they worked with me. So this is a gentleman from General Motors who were kind enough to fund some of this work, and Jayakrishan Nair was in PhD student in Caltech and spent a summer with me. This guy was in India and was a summer intern also. This guy was my student in IIT, and this is a colleague from ISC, and various parts have been supported by various kind souls. With that, I stop.
Thank you very much. Any questions?
Maybe just a hunch. I'm just trying to think about how to evaluate the first part of the talk, about how you choose the best
Keynotes.
the best version of relative value iteration. And my hunch is that if you look at like a special case where the second eigenvalue is really close to 1, it might be, I feel like almost anything you do, your resulting rate of convergence, top eigenvalue will be lambda 2, will be the second eigenvalue. You know, I just wonder, I don't know, that's just sort of a guess.
I mean, instead of Vi naught, if I want to choose
Almost anything you do, you're going to get the top eigenvalue of the new matrix is the second eigenvalue of the original one.
Oh.
I mean, I think you can imagine how I see this. But have you looked at that? I mean, which would mean it would be a very insensitive problem. So almost anything works optimally. So I don't know. Have you tried it out? Have you?
No, I haven't thought about it.
Interesting to see.
Questions? Just a short question, if I may ask. You mentioned the result by Hirsch on cooperative differential equations. In what context had you done that? Was that related to K theory or?
No, that was this nonlinear equation which I had. So sorry, what's the question?
No, the question is the original work of Hirsch was.
I don't think that was in any context as such. They were studying cooperative and competitive ODEs. And cooperative ODEs lead to monotone dynamics, and if the trajectories remain bounded, then for almost all initial conditions they converge. So this is a book by Smith called Monotone Dynamical Systems, does this in great detail.
Thank you. Thank you very much.